Ever wonder why satellites don't just crash back to Earth? From our perspective down here, they look like tiny, steady pinpricks of light, drifting through the void with a kind of eerie, perfect stillness. It's easy to assume they're just hanging there, tethered to us by some invisible string, or perhaps just floating passively in the vacuum. But that's a beautiful lie. In reality, nothing up there is actually still. They aren't floating, they are falling. They are in a state of permanent, high-speed plummeting, hurtling around our planet at thousands of miles per hour. It is a frantic, kinetic dance of physics where every single second is a battle between the relentless tug of gravity pulling them down and their own incredible forward momentum trying to fling them off into deep space. They are essentially caught in a cosmic stalemate, a perfect, delicate balance where they're constantly falling, yet forever missing the ground. Now, to understand why they don't just crash immediately, we have to talk about the relentless, invisible tug of gravity. It's the great cosmic glue. If you were standing on the surface of the Earth, you wouldn't feel it as anything more than the weight of your own body. But up there, in the silence of vacuum, gravity is the conductor of the entire show. It's pulling on every single satellite, trying its absolute hardest to drag them straight down into the atmosphere. If gravity were the only player in the game, every satellite would become a shooting star within minutes. But they have a secret weapon, velocity. They are moving sideways, incredibly fast, thousands of miles per hour, with so much momentum that as gravity pulls them toward the curve of the Earth, they essentially overshoot the planet. They're falling, yes, but they're falling around the bend of the world. It's a high-speed chase where the Earth is pulling and the satellite is running, and they're locked in a loop that never ends. To understand why they don't just crash straight down, you have to imagine a very specific, very delicate kind of tension. Think of a giant, invisible tug-of-war. On one side, you have gravity, the relentless commander trying to pull everything back to the surface. On the other, you have inertia, the natural tendency of an object to just keep going in a straight line forever. Back in the 17th century, Isaac Newton intuited this with a brilliant thought experiment called his Cannonball scenario. Imagine you're standing on a high mountain peak and you fire a cannon. If the charge is small, the ball curves and hits the ground a mile away. Fire it harder and it lands much further. But Newton realized that if you fire it fast enough, really incredibly fast, the ball will travel so far that the Earth's surface actually curves away beneath it. The ball is falling, yes, but the ground is dropping away at the exact same rate. It's falling around the world, perpetually missing the Earth. But here's the catch. That perfect, delicate balance, that sweet spot where gravity and momentum shake hands, isn't a static thing. It's a constant, high-stakes tug-of-war. You see, if you go too slow, gravity wins. You lose that frantic forward momentum, and you just crash. You become a crater. But if you push too hard, you break the leash entirely. You outrun the Earth's pull and drift into the lonely, freezing dark of deep space. So, engineers have to calculate this velocity down to the last millimeter per second. We aren't just talking about fast. We're talking about 17,000 miles per hour. Imagine trying to throw a baseball, and instead of it hitting the grass, it just keeps looping around your head, forever. It sounds like science fiction, but it's actually just a very precise mathematical dance. It's the art of falling without ever hitting the floor. And once you find that rhythm, the satellite becomes a permanent resident of the sky. But not every resident stays at the same altitude. In the hierarchy of space, distance is everything, and where you sit dictates exactly what you do. Most of the heavy lifting happens in low Earth orbit, or LEO. This is the frantic, high-speed neighborhood, just a few hundred miles up. This is where the International Space Station lives, hurtling along at nearly 17,000 miles per hour. It's crowded, it's fast, and it's essential for high-resolution imaging and low-latency internet. But if you want to stay perfectly still relative to a person on the ground, you have to go much, much higher. You have to climb to geostationary orbit. At about 22,000 miles up, the satellite's orbital period matches the Earth's rotation exactly. To us, it looks like it's hovering, fixed in place like a steady beacon. From Elio, we get the details, but from Geostationary, we get the big picture. It's a tiered system of altitude, each layer serving a specific purpose in the vast architecture of our connectivity. But to understand how these layers actually hold their shape, we have to look past the silence of space and see the invisible highways of orbital mechanics. It sounds like science fiction, but an orbit is really just a high-stakes game of falling. Imagine throwing a baseball. It travels a bit, then curves, and hits the ground. Now, imagine you're standing on a mountain and you throw that ball so hard, so fast, that the ground actually curves away beneath it as it falls. The ball keeps falling, but it never hits the ground because the Earth is literally rounding the corner. That's an orbit. It's a state of constant, controlled falling. For a satellite to stay in that sweet spot, it has to balance its forward velocity against the relentless tug of gravity. Too slow, and it tumbles back to Earth in a fiery streak. Too fast, and it breaks free, drifting into the void. It's a delicate, mathematical dance, where speed is the only thing keeping the sky from falling. But that brings us to the question that's been bugging you since you first looked up at the night sky. If everything is falling, why don't we? Why doesn't the moon just crash into us? Or why aren't we being pulled off the ground by some celestial magnet? It feels like we should be sliding toward the center of the Earth at terminal velocity, yet here we are, perfectly anchored. The secret is that gravity isn't just a downward tug, it's a constant, relentless curvature of space itself. Think of it like a heavy bowling ball resting on a trampoline. It creates a dip, a slope that everything else naturally rolls toward. We aren't staying up so much as we are caught in a permanent state of falling, perpetually missing the ground because our forward momentum is so perfectly balanced against that downward pull. We're essentially falling around the Earth, stuck in a cosmic loop that never ends. It's a beautiful, terrifying tension, the balance of being held and being let go, all at once.